I presume you can see this then?
Yes, perfect. Yeah.
Okay,
Okay,
fantastic.
Thanks.
Let's begin. So in this talk, I'm primarily going to be speaking about some observations and research that isn't in any papers then. So consequently, I guess it's a workshop exclusive. I'll first talk about spurious cues and how I think that is an overwrought story for characterizing why models are brittle. And then I'm going to talk about a different lens, which I think is more useful for explaining why models are fragile. So before starting out, let's just set the stage by looking at some benchmarks demonstrating how models are fragile in adverse weather conditions, for instance. So while a ResNet 50 might get 76% IID accuracy on each of these different corruptions, when it hasn't seen these corruptions during test time, this is the sort of accuracy that it's getting. So consequently, as you can see under snow, you've got approximately a 50% accuracy drop. So quite severe. There are other types of distribution shifts that we can also pay attention to. One would be by hard example mining. So maybe you saw Andre's talk earlier this week, where the process is primarily deploy the model, see what it's getting wrong, label the things that it's getting wrong, and continue that loop. So we can simulate one of those loops with this adversarially curated data set where we adversarially mine examples that a ResNet 50 gets wrong. And then we observe that the examples that a ResNet 50 gets wrong, lots of other models get them wrong as well. Even vision transformers have fairly low accuracy on this data set too. So one round of hard example mining shows that accuracy can really degrade, and the faults that hard example mining expose are consistent among models. Even if you change your pre-training distribution to something like Places 365, if you change your architecture to a vision transformer, still the accuracy is pretty low. A third, more exotic type of distribution shift would be testing generalization to renditions. So for renditions in ImageNet, they instructed the labelers not to include any photographs or anything like that. Meanwhile, we collected the exact opposite then. We only collected things like photographs and renditions, things of that sort. So, so this drops accuracy by like over 30% on basic ResNet. So they're not robust when they're seeing some of these types of rendition shifts. So this is some way in which we've attempted to characterize the space of different distribution shifts, and we'll use these in some of the later slides. But first, but now let's consider what's the cause of the brittleness. We saw that all these different things are making the models mess up in kind of unexpected ways. Well, a story that goes back a long time ago in machine learning, is somewhat of a folk story, possibly apocryphal, is if we're trying to classify tanks, one data set of tanks had the images taken when it was brighter, and another set of tanks were taken when it was darker outside, or maybe when there were clouds, something like that. And the model didn't actually learn to classify the tank based on the shape or anything like that. It just paid attention to the brightness, so that would be an example motivating that they might just be learning some spurious artifacts and not actually learning what they should be. Another example of this is maybe networks will rely very heavily on background, such as snow in the case of determining whether this is a wolf or not, instead of actually paying attention to the wolf-like characteristics. I should like to argue that the shortcut features and these spurious cues are a lot less compelling than I initially expected as an explanation for fragility. So hence the quote, I think it would be important to de-emphasize the story and not look at it if Jerry Sussman's advice is right. So let's see how the spurious cue story starts to break down. We can consider a very simple context. Let's just to look at CFAR images, for instance, and then let's add some spurious cues. So what we saw earlier was that brightness is apparently class, it can be class indicative. So what we'll do is we'll make all members of a class have the same level of brightness, something like that. So we're modifying the data synthetically to inject some class indicative features and see whether the network will actually even learn the class indicative features. So in the second type of cue that we implemented, we just have some colored pixels, and the color of the pixels indicates the class's identity. In the third, we have some class-specific noise. So every member of a specific class in ImageNet, say in this case the deer class, has the same noise added to it. And other classes have different noise. So will the network start to learn whether it's actually a deer, or will it just start to memorize the noise statistics? And the final one, this is a 6 in the bottom right. So here's a frog, and then we have a watermark that's just saying directly what the class is. So will it latch onto that accidental label leakage, or will it actually learn the correct thing? So what we observed is that the class-specific noise can get really small. So it's possible for these to learn very subtle statistics, interestingly. Meanwhile, the images are between 0 and 1. The noise is very small. So this does demonstrate that it is certainly within their capacity to find lots of features that are invisible to the human eye and pick up on them. However, if we have only 80% of the examples have this dead giveaway cue, then the accuracy goes from something like 4%, or excuse me, the error rate goes from something like 4% to 17.7. So 0 is 4%, 80% to 17.7. When you have it be 100%, if all examples have the spurious cue, the exact same spurious cue, in each class, then you get to random chance levels, because 90% is 90% error rate is random chance on CFAR. So if we don't have it occur all the time, it's not nearly as severe. And 80% consistency for a spurious cue, I think, is already fairly high. You'll see objects in different conditions, different lighting conditions. There's a lot of variability between the examples. So a cue being omnipresent seems fairly artificial. Let's consider the case of brightness, for instance. And let's consider doing CFAR 100. What we would then need to do is, if we're to argue that brightness is a cue, then if we're to do this in a simulated way, we would need 100 different brightness levels, and each one only matching one class. And they're not being like overlap among them, so, or else that would distort the signal. So if we have lots of classes, and if we're trying to inject spurious cues, it gets kind of difficult. So it's very easy to inject spurious cues if you've got 1 or 2 classes. One class is much brighter than the other one, but if you've got lots of classes, a lot of these concepts are going to be overlapping, and that makes the story that spurious cues are going to be very class specific and be giving away a specific class, so harder to maintain. I'll come back to that a bit later. So how do we reduce the error rate when assuming that the spurious cues are actually omnipresent? Well, some things didn't work. If we do something like elastic wave consolidation or adversarial training, and adversarial training is supposed to improve robustness of some sort, yeah, that doesn't really help with anything. However, we tried some different techniques, and the results below are for all 4 omnipresent cues, not when they occur at 80%. If they're occurring 80% of the time, it's too easy to resolve. So we'll just tackle the hardest one, when the spurious cue is perfectly reliable and will always be giving away the class's identity. If we train from scratch, we are at, excuse me, this should read error rate, not accuracy, my mistake. If we're trained from scratch, we're at 90% error rate. If we do pre-training, that is, if we pre-train these models on ImageNet, and then fine-tune them on CFAR, which is, of course, a paradigm that we're all adopting. We're all adopting a pre-training paradigm here and in practice. Then the error rate goes down to 17%. I can then add some different types of data augmentation. Mix-up doesn't really help. It makes it a bit worse. Cutout helps a bit. Mix is even better. If we use augmix, a method from iClear 2020, then the error rate basically gets near to the level when there are no cues at all. So it was kind of easy in this very worst case situation to overcome the issue, and just pre-training alone did that too. This makes me fairly skeptical that spurious cues are that much of a challenge. They certainly contribute to it. I mean, observe, there still is somewhat of a gap here in this very extreme scenario. So it's not like we completely solved it, but for all that, I don't think it should be the primary story motivating the study for robustness. So let's revisit this a bit further. It doesn't seem that brightness is a plausible cue, especially when there are many classes. As they train on more classes, as they pre-train on more data, and as more data augmentation is used, it seems that the models become more resistant to spurious cues. And likewise, a lot of the experimental designs that people are using, such as say colored MNIST, when they're doing like binary classification and not using pre-training and not using data augmentation, I think we have some reason to doubt the ecological validity of these tasks, because they, in many ways, when you add some more realism for what the pipeline actually looks like, a lot of these problems start to vanish. So I'd like to return to this circulating figure, or popular figure showing an explanation for what the model is relying on in trying to determine whether an example is a husky or a wolf. And this task, I should note, for this visualization, the model trained on 20 training images. This isn't actually a realistic proof of models needing, or models relying heavily on spurious cues. And also, there are many ImageNet classes with snowy backgrounds. So if we were training on many diverse classes, they wouldn't be thinking that, if I see snow, that means wolf. That wouldn't be a reliable feature anymore. Sure, it will build some sort of association, but the association will decrease as it sees more diverse settings and different objects in different backgrounds. It sort of gets partly gets washed away as it starts to train on more data. So I think some of these stories we should be much more skeptical of. So I'd then like to present a different view, which I think other people are taking up, especially in the autonomous vehicles community, which is that what we're actually dealing with is we're dealing with black swan events, extreme events, or some other characterization of heavy tail or long tail events. So for instance, here's some examples where somebody's driving on a road, but there's another person who has a horse, or although there's a green light over here, there's a fire engine, or there's an ambulance going across the street, so you better not drive. These types of events, hard to predict. Basically, two or more things factors start to collide that would normally be thought independent, but they end up interacting in a way that's fairly unexpected, and that really throws us off. These combinations happen infrequently, but when they do happen, they can be pretty devastating. It's very hard to model. So just to see that, I think that these heavy tails are actually pretty common, and why they're probably common for a lot of robustness contexts is we can see that they're common by just seeing many instances of them elsewhere in the world. So for instance, intensity here, intensity is actually the number of deaths in armed conflicts divided by the population of the combatants. And we see that follows something like a power law. And the heavy tail ones, with heavy tailed events, the frequency certainly decreases though, but the intensity also increases when they do occur. Other examples, I suppose, maybe of interest to academics would be citations. There are a few people at the extreme end who've got lots, and then there's a pretty long tail, very skewed distribution. So a small fraction of events end up accounting for a lot of the variance in the distribution. And so this is, we can see that these events are pretty common. Now, one sort of way of seeing how these might arise is there are different models for how heavy tails might arise. One might be a multiplication of lots of different random variables. So if we multiply lots of different random variables together, then we can end up with a log normal distribution, or maybe a Pareto distribution, depending on whether the inequality is strict or not. So in this case, it's something like a log normal distribution. Now, note, if we, of course, added these variables instead, we would, by the central limit theorem, have a normal distribution. So the key difference between normal distributions, which we're very comfortable with, and log normal distributions, which are hardly taught in statistics courses, is that rather than there being addition, there's multiplication. So now, how can I tell whether I've got a normal distribution or a log normal distribution? Well, question whether the interaction is multiplicative or whether it is additive. So in the case of weather, if the brightness becomes 0, if we can't see anything, that's not an additive effect. You can't see anything. Your perception has completely diminished. You can't do anything anymore. So that is something more like a multiplicative effect rather than just an additive effect. Likewise, the intensity of snowfall or the thickness of fog, all of those seem to have more of a multiplicative property in the quality of perception rather than just something additive. So I'd like to further impress that our intuitions for heavy tails are not very well developed by taking typical statistics courses. So let's consider this example here. If we've got a Gaussian distribution, we've heard, maybe we can get 30 examples. And once we have 30 examples, we can estimate the mean with some fair reliability. The means quality variability reduces by root 30 or 5.4. But now let's consider an 80-20 Pareto distribution. This is the one used in lots of common examples, like 80% of the land is owned by 20% of the people, 80% of the complaints are from 20% of the users. This very common distribution is a Pareto distribution that is heavy tails. And I suppose the question I should like to pose to you all is, how many samples do you need to reduce the estimate variability of the mean of this distribution by a factor of, say, 5.4? In the case of the Gaussian distribution, we needed 30 samples. Now, it's not 300, it's not 3,000, it's not 10,000. The number of samples that you need is actually more than 1 trillion. Okay, and this is a one-dimensional distribution that you're dealing with. So this suggests that one, our intuitions about long tail events we're kind of underestimating how difficult they can be. And this is, I suspect, one reason why we keep making such wrong predictions about autonomous vehicles. We don't know how hard or how thick this heavy tail actually is. It's many orders of magnitude worse than we sometimes expect. Note 1 trillion examples. I should note that on ImageNet, or excuse me, on the latest vision classification models, they're trained on maybe the Joint Photo Tree Bank, which has fewer than 3 billion images. So you're going to need another 3 orders of magnitude. If we're just pretending it was a one-dimensional distribution, we're just trying to learn something basic about the distribution, like the mean or something like that. So anyway, we don't have 1 trillion examples lying around for a distribution as relatively benign as this. This is still one-dimensional. It's not even high-dimensional. So what can we do? Well, some things we can do is simulate more extreme events. And this seems to be a fairly effective way at combating the issue that we may not have enough data. So in this plot, I'm showing the result of 2 different data augmentation techniques mixed together versus training on 1,000-fold more data. And this is with the ResNext weekly supervised learning model. And what we can observe is that the robustness of the model can greatly improve with just data augmentation. And we can improve its robustness to distribution shift and end up beating out the effect of training on 3 orders of magnitude more data. So anyway, data augmentation will be indispensable to us, though. There is an issue of us needing to find sources that are not too sterile. If we just use Gaussian noise as an augmentation, sorry, that doesn't have enough complexity. It's not just about the descriptive complexity of the stochasticity that you're going to throw into the system, which Gaussian noise has high descriptive complexity. It's also the structural complexity, something like the fractal complexity. How chaotic is it? These types of things. And for that, we haven't been doing, I think we haven't been doing enough research and coming up with these richer simulated scenarios and data augmentation techniques. Some other things we can possibly do are of course, collecting more data should help, but we will need other methods. Maybe online domain adaptation can be a partial patch. However, we can't assume that the distribution will be steadily shifting. With black swans, it's much more sudden. The ambulance pulls in front of you all of suddenly. It's not something that happens very slowly. It happens over, several hours. So the volatility and the stressor applied to the system is lumped together. So our online domain adaptation benchmark should probably capture the fact that volatility and stressors happen much more suddenly. And I think finally, it would be good to characterize the thickness of heavy-tailed distributions so we can see just how hard some of the distributions that we're trying to encounter in the real world really are. So here are, here's on the left is something like a CDF, and then this is the prediction confidence in the correct class. We can see if the prediction confidence is like something like 10 to the -7, the model is very wrong. So we can see its prediction confidence in the correct class is heavy-tailed. That is to say, it makes some very bad errors in a heavy-tailed like way. I don't know, this is some attempt at characterizing the how heavy-tailed some distributions are. As we can see, some types of distributions like Imagine A and R are much harder to, or have worse heavy tails. Meanwhile, just adding noise to it doesn't seem to change the heavy tail property that much of the image. So this is one attempt at characterizing how heavy tail distributions are, but I think it'd be very good if we could characterize what's going on in these situations. What is making them be more heavy tailed? Our characterization would need to be model dependent, but I think that would be a pretty fruitful type of phenomena to quantify so that we know what we're up against and how much data we need, and whether methods are making the models respond differently to some of these events. So that would be good to have some more precision on. So in summary, I don't think the spurious cues and shortcut story explains all of the fragility. I think it accounts for some of it, but it's currently, I think, being a bit overemphasized. Instead, what a lot of people working on autonomous vehicles are focusing on heavy tail events, black swans, extreme events. I think that's a more promising lens. And in view of that lens, we should work on more data augmentation to sort of importance sample the extreme events, improve domain adaptation test beds to account for the fact that volatility is lumped together, and also attempt to quantify the thickness of the heavy tail distributions that we face in practice. So with that, I'd like to, what questions do you have?
Yes, thanks. Thank you, Dan, for the great talk. So are there any questions? Maybe I can ask one. Oh, is there any question? I saw that someone wants to speak. Or... Okay, I think, I mean, I saw that people actually in the community actually using in data augmentation policy quite, let's say, quite often. Sometimes people use it very aggressively in a sense that, so in the end, I mean, at some point, do you think that we will actually have to come back to address the problem caused by data augmentation strategy? Or, I mean, this kind of data, I mean, it's quite, this sensor size augmented data, it's quite realistic, but of course it have its own issues, problem, right? So what is your opinion, like where, how long we should try on this augmentation, or like what is the future, let's say?
Yeah, so we see that it isn't helping with some of these more structural shifts, like if we're changing geographic location. So I think there's a lot of richness that they'll need. Of course, in the past, it's been quite difficult to simulate realistic things that are informative for models, but deep learning is getting better at modeling more realistic scenarios and generating realistic data. So that's some, hopefully we'll have more of that. It seems that there's still pretty active development in data augmentation. So it's something, I don't think it's crowding out other research efforts. I think also most of the data augmentation techniques are not developed in view of robustness to distribution shift. They're still just trying to improve IID accuracy. So I don't think they're even exploring their robustness properties that much. So I still think it's relatively under incentivized, and that there's low-hanging fruit. So
yeah, thanks. I see there are two questions in the chat. So so the first question is, to what degree can we have an automated or unsupervised way of finding what issues manifest themselves in the long tail and how to simulate them? Or is there no substitute for domain knowledge? For example, we know we need to simulate heavy weather. It's quite long that maybe we also see from the chat that
so there are some, so I guess in response to that, there are many domain or data augmentation techniques, for instance, that don't explicitly incorporate domain knowledge, but will still help with generalization to them. So for instance, it's very hard to model like the rendition distribution shift synthetically. Nonetheless, the data augmentation techniques help quite a bit with that type of shift, even though it isn't baking in the many assumptions about what the distribution shift is going to look like. So I think there are some techniques that are fairly general, will help you in a lot of these cases, and you don't need to. It's also quite difficult to model a lot of black swan events. Certainly you can get at some, but there are like black swan events in the real world would include like COVID or the financial crisis or things like that. These are pretty tough to model and can be pretty unexpected. Still, what you can do to improve your system, like the overall system in view of these events, is to reduce its exposure to risks and decrease the extent to which it deteriorates under volatility. And so we'll just have lots of stand-ins for volatility, get a very diverse set of that, and see whether you're generally improving its resistance to volatility. And some of that will generalize and help us whenever we're faced with some completely novel events. As we've seen with data augmentation, that sometimes helps with completely novel events for which it was not designed.
Yeah, thanks. There's one very specific short question about what do you mean by shortcut features?
So there are different characterizations. It might be like there are features that humans wouldn't rely on that are highly class indicative or something like that, and that the model's doing. Some people might make it more broad and say they're wrong features, but that's not really adding any precision to the discussion if we're using that vacuous of a definition. What's the explanation for why we don't have good video understanding? Well, it's because of shortcut features or spurious cues. You know, that's not adding clarity. So I think it's things much more in the vein of some background feature or some information leaking in an unexpected way. Maybe this class was taken with this type of camera, so the sort of lens had some like very subtle artifacts in how the image appears, and the model is classifying images in view of the by just looking at the sort of picking up on the subtle lens information. Those sort of things are what people are meaning more by spurious cues and shortcuts.